And with the combined expertise, we try to break electronics in popular use that promises security, but is oftentimes outdated to the point where we think it should be broken or at least breakable, and want to show that. And oftentimes, as a result of this research, technology then does get replaced, modernized. I want to today talk about a technology that has been criticized for a few years now and that hasn't seen very many upgrades yet. I specifically don't want to release any new hack or further the skill of breaking these particular devices, but rather I want to use this opportunity to summarize what has been done over the years, because so far the information around the topic that I chose is a little scattered and hard to interpret, ranges from anywhere I can steal any car in the world to all cars are protected, at least from what's publicly known. And of course, there's always the truth is somewhere in between. And I want to use this talk to explain the structure of this market that I'm talking about, car immobilizers, the elektronische Wegfahrsperre. Yeah, not everybody knows what immobilizers is. I certainly didn't a few years ago. I also want to use this opportunity to illustrate using immobilizers how a cryptographer approaches a proprietary system, in hope that some of you who may have come across proprietary cryptography get a deeper understanding on how to analyze and how to perhaps break them and show them insecure. Sounds good? So I'll start by providing some background on how these immobilizer devices are supposed to work, what the protocols are, and so forth. I then want to dive into showing how every single instance from all the different manufacturers of immobilizer devices carry pretty drastic vulnerabilities. However, I don't want to argue that most of these vulnerabilities are somehow covered by other dynamics of these systems, so they don't actually lead to the equivalent of exploitation, which for an immobilizer would be a stolen car, of course. And I then want to close with an example of how cars do get stolen in the real world, and show that we as researchers may have looked at the completely wrong topics for many years, while some Bulgarians just developed their own tools apart from any open research, and today steal any car they choose. And from there, of course, I want to motivate more research into exactly those areas, so that we as an open research community are closer to what's actually happening in the world. All right, immobilizers are, as far as I understand, the first use of cryptography in cars. They are found in pretty much any car today. Even older ones on the street have been in cars for 2 decades now, and they are what makes your car key have this plastic part. A lot of keys are just metal, like your house key, but car keys are almost always plastic as well. And inside the plastic, there's a little chip, right? I used to have a car that still had just metal, but those tend to disappear now. Probably whoever here has a car, you've noticed that it has plastic, and you can even test that it has an active component in it by wrapping the plastic part in foil. Your car won't start anymore, right? Because the communication is radio and it's hindered by that. Those devices are meant to make it harder to steal cars, and they were extremely successful. They came in 2 waves. One, kind of the naive static signature type transponder, usually magnetic signatures that didn't have enough entropy and were easy to spoof. But even those deterred theft early on, until the thieves figured out how to circumvent those devices. And then quickly after cryptographic means of protection were introduced, that again the fraudsters or thieves had a hard time circumventing, and in fact probably haven't really circumvented yet. So these really do build on good cryptographic protocols, most of them, however, with bad cryptography in a lot of cases. It turns out that this is from the FBI, after they stopped publishing these numbers, the theft rates went up dramatically. Not so much because of bad immobilizers. I'll get towards the end of the talk into the why that is. In Berlin alone, for instance, last year had a spike of some 27% in car theft, and that's almost entirely attributed to luxury cars. So not only do people steal many more cars, they also seem to choose which cars they want, and of course go for the most expensive, you'd think, best protected cars. So there's waves of car theft where one model then gets stolen in the hundreds and supposedly moved through Eastern Europe to somewhere else and taken apart. Now, I want to talk about the technology behind it, and then later on talk about a little bit the market dynamics and what technology components may also contribute to weaknesses. But let's for now focus on immobilizers, these little chips in the plastic part of your car key. These little chips, they have a counterpart in the car, of course. It's a two-way communication, often anchored in the engine controller that then talks through an antenna close to the steering wheel to the car chip. Sometimes that chip is also next to the steering wheel, depending on model and supplier of the chip. But there's always a secret key involved that's used in a challenge response, two-way challenge response protocol. The first challenge is to prove to the car that the right key is present. That's of course needed so the car starts and is not stolen by somebody who doesn't have a key. And that's the core immobilizer functionality. It's an extremely simple protocol in which the car sends a random number in it once in a certain time frame. The encrypted version of that random number, it itself can generate the same encryption, compares the two, and if it matches, the car starts. And every time it's a new random number, so always the right key has to be present. It then also authenticates the key somewhat unintuitively. You'd think that the immobilizer functionality is done at this point, but the car wants to write data onto this chip. On every car start, pretty much any immobilizer puts data onto the key, for instance, the current mileage. And that's, for instance, used when the car gets stolen. You want money from the insurance company, and the amount of money depends on how old the car was, but also how many miles, kilometers it has driven. That's stored on the car key, right? So you hand in your car key to the insurance, and they figure out the value, right? So that's why there's a two-way authentication, so that not anybody can write data into these keys, but only the right the car that's supposed to. Make sense, right? And this is important. We'll get later into a weakness that arises from an optimization to this three-way handshake, so to speak. So that's the basic idea. And while all the different chips build up on the same principle, they vary by manufacturer. There's three main manufacturers. Texas Instruments used to be very popular with a 40-bit version of its chip in the US with a bunch of manufacturers, and also Toyota, I think. After Johns Hopkins University showed those insecure, many of their customers moved away to other technologies, partly to the successor from Texas Instruments with a much larger 80-bit secret key. Some moved to the most popular immobilizer, formerly by Philips, now NXP. It's called High-Tech 2. There's also High-Tech 3 that found adoption in the last couple of years. So I'd have to edit here once I again run this research. And there's a third manufacturer out of Switzerland, EMicro. They usually build smart cards, and they also supply this immobilizer. That's not used by a large number of brands, but they have a large number of cars. So this is pretty prominent in the market. And so the market is pretty much divided between this technology that uses a 40-bit key, this technology that uses a 48-bit key, and this technology that uses a 96-bit key, right? So in kind of internet age-type cryptography, all of these sound ridiculously low. We're not used to anything below 128-bit keys, right? That, of course, would be the first vulnerability by design that these transponders share, and that's also the first vulnerability that I want to discuss in a little bit of detail. John Hopkins, that university that showed the Texas Instruments chip insecure, all they did, it was a lot of work, but still all they did was figure out how this transponder works. And once you understand how a 40-bit encryption system works, of course you can break the key. You just try all of them, 2 to the 40 chips. And they used an FPGA cluster similar to this that they built themselves. And it took them 1 hour with, I think, 8 medium-sized FPGAs. This is back in 2005, to break 1 instance. Back then, they were not targeting cars primarily. The same chip was also used in a payment system by, I think, ExxonMobil. So you could pay your gasoline at the pump with a little transponder on your keychain, and they broke this. And of course, breaking 1 instance of a payment system device in 1 hour, that's valuable. That's a realistic attack. With a car, not so clear. Is the car still there an hour later? Do you have an hour in between breaking in and actually wanting to start the car? But focusing on just payment, they definitely showed this insecure. And as I said earlier, a lot of people then migrated out of the 40-bit version. Now, the closest competitor to this 40-bit chip is the 48-bit chip by NXP. And as cryptography goes, every bit that you add to a key makes it twice as difficult to break it. Right? So 8-bit, figure out yourself how much more difficult that is and how many of these devices you would then need. If for 40-bit you need 8. So that's a full room of not so cheap devices. So one could argue that 48-bit may actually be enough to protect the device that, an hour later probably already drove away, or at least you don't want to go there again when somebody may have seen you break in an hour earlier. So you'd need a whole bunch of these devices to break it. Or you'd need a different approach to breaking it. And that's now where deeper understanding of cryptography comes in. The brute force approach here requires no knowledge whatsoever. You find a cipher, you try all the keys, one will work. If you do have a deeper understanding of cryptography, you start asking whether there are shortcuts in the function. And that's then usually referred to as cryptanalysis. And most good ciphers today, nobody has any good idea how to do cryptanalysis, but for some older ciphers, new ways of cryptanalysis are invented all the time. We looked at this high-tech 2 cipher, the one was 48-bit, the first time, I think 4 or 5 years ago, and there was no obvious cryptanalysis tool you could apply to this, because not because it was resistant to them by design, but because the cipher was too different. It looks like this. It's a linear feedback shift register. So if you think in software, this is a register, 48 bits, and in every iteration of the cipher, and every clock cycle, you move all the numbers in this shift register 1 over, and then you XOR a few of the bits and move it in the first spot, the empty spot, that emptied when you moved everything along. And now think about executing this symbolically. Everybody knows what I mean by that. Kind of instead of working with numbers, you work with symbols. Let's say ABC all the way to whatever the 48 stand is. And you move all your numbers, and then you put in the first spot something like D, X, or F, X, or whatever, right? And you keep doing that. You work with the symbols. The insight here now for a cryptographer is that the complexity of these equations is very limited. the most you'll ever get by XORing a collection of 48 different symbols is a string of 48 things XORed together. If you want to XOR anything more into this, it will have to cancel something out that's already in there. Makes sense, right? That means the equations that are behind just this part of the cipher, they're extremely simple to solve. It's just linear, and they can only have 48 terms. That's nothing for a good solution solver. I mean, software, not a person. And then to add a little bit of complexity nonetheless, what the NXP cryptographers or Phillips cryptographers then did is put this very big binary function. It's just a gigantic lookup function, but realized in hardware where you can actually produce it very small, to take a bunch of these bits, these chains of XOR of the original 48 unknowns, and jumble them up together. And they do a good job. So for something that only takes 20 inputs, this is kind of the maximum you can get out of it. But that's then where the cipher outputs its information, right? So there's no possibility of the added complexity that is created in this step to add up. Kind of if you went through this multiple times, you can see how if you put into a big lookup table a very long symbolic expression, the lookup table will make it longer and longer and longer and longer, up to the point of having the theoretical maximum is 2 to the 48 different terms. So your first term is your A, your second term is B, your next term is C. After those 48, you have a term that is A and B, then you have a term that is B and C, then you have a term that is C and D, and the term all the way at the end is A and B and C through 48, right? So that's a total of 2 to the 48 things you can choose from for your equations that make the equation possibly extremely long. So long story short, we create the equations for this cipher that have only linear terms down here and then a little bit of added complexity, and we throw them at a solution solver. Remember, our goal is to use less computing hardware than hundreds of these FPGAs, and perhaps we want to even break it in less than 1 hour, right? And when we solve this, we use what's called satisfiability solvers. And my colleague Matej Soos, he programmed one of the leading ones, but it's all open source, so you guys can use those right away if you have any system of equations. And when it solves it, it looks like this. This may be a little bit hard to read. Let me try to zoom in here a little bit to show you how to zoom here. Oops. Oops. So you see how this is a tree of steps the solver did to try to find the right solution. And how do you find a right solution with an equation solver? In this case, it uses the simplest possible way. It guesses values. It says, maybe my A is 1. And then it puts that in all the equations it has. And some of them become simpler. Some of them may go away. Some others may shrink to the point where it then says, okay, if A is 1, then C is 0. Right? So it learns. The equations become shorter. If you were to guess all 48 of them at the same time, then you'd have a kind of yes, no, it works out or not. But that's brute force again, if you guess all 48 and go through all possible ones. So you guess only one at a time, and you do what's called propagation. From this node, you guess something, and then you reach, where does this go? Down here somewhere. And this now is another instance with shorter equations, but also with the assumption that A is 1, which may or may not be true. And then you keep going. You guess the next one. You say B may be 0. And again, your equations become shorter and shorter. And eventually, you either know that you guessed right, but in most cases, of course, you didn't, and you reach a contradiction. It says, if that is the case, then D is 0, but also if that is the case, D is 1. So different equations come to different conclusions. And that's when you know something was guessed wrong. And let's say you guessed 3 things up until then. right? Then you know that you must never guess those 3 things in this same constellation again. So if ever you reach a point in the guessing tree again where you already guessed 2 of them, you know what the 3rd one must be. It's kind of a forced guess. You pruned the whole branch of this tree, right? And not just one. Wherever these 3 occur in sequence, or not even in sequence, just somewhere in the already guessed chain, then you prune the rest of it. And that's just after the first failed attempt. And so in this picture, you see how this goes all the way down here, guessing, something like 30 things it guessed, and then it reached the first contradiction. It goes back and it guesses something else. Again, it reaches a contradiction. Every time it kind of ends a branch here, it reached a contradiction. And you see how as it learns, and it learns more contradiction, it doesn't have to go so much down the tree anymore. It learns information. And if you add up the different guesses on this slide, there are a couple of thousand. This is all the guesses this solver had to do to then have enough contradictions to be kind of guided through the guessing tree to the right one. And that's, of course, the one where it went all the way down here. This is when it guessed all 48 correctly, right? So you do this instead of 2 to the 48 random brute force type guesses. And this runs on a CPU in, let's say, a minute, right? Instead of on hundreds of FPGAs for an hour. And that's not because the key is short. That helps. That means we only have 48 things to work with. But that's because the cryptography behind it is flawed, right? So that's what probably you can also try against the DST cipher from Texas Instruments and make it even faster than those FPGAs. We have tried that. We have failed. So the Texas Instruments cipher has a very weak key, but it has a good cryptographic structure. Moving from there to 80 bits, what they did may actually have been a great idea. Take something that is structurally good, but has a too short key, extend the key. Now, I don't want to propose using anything proprietary. Moving directly to AES would be an even better idea. But as far as this market goes, nobody seems to want AES because then everybody can build something compatible, of course. Building a strong block cipher like Texas Instruments did and bumping it up to 80-bit is definitely better than using a flawed stream cipher that even at higher key lengths can be solved like this. So everybody understands how this tool works and how you can, if you find a cipher, apply this, right? Write out all the equation, not yourself, but write a program that does it, and then have these megabyte files of equation, throw them at an equation solver, and it will smartly choose whatever it has to guess, remember things, and then prune the tree until only one branch is left. All right? So this, of course, also is defeated by much longer key sizes. This saved us maybe 30 bits of complexity, so it brought the 48 down to, let's say, 18. Right? If we had a much longer key and it again saved us 30 bits of complexity, that may not bring it to a point where we can easily break it yet. And that's then the area where the third cipher, the MegaMOS cipher, would be king. It uses a 96-bit key, so twice what's here. And even if it had the same cryptographic weaknesses that this had, that saves us 30 bits of complexity, that's not enough yet to even brute force it. 60-some bits, then that's still a little bit too much to steal a single car. However, don't want to get into the exact details here. 802 has cryptographic weaknesses that are solvable this way, but much, much more difficult than the high-tech 2. I want to drive the discussion, though, to another point, and that is incentives for attack. This 48-bit cipher has been broken many times by many researchers and FPGAs with SAT solvers as we did with many other methods. However, not a single car has ever been stolen using this method. Why? Remember the original challenge response protocol. What does the car give you initially? A random number. And what type of cryptanalysis can you do on a random number? Nothing. Right? So despite all of this, despite FPGAs breaking 40-bit keys and SAT solvers breaking 48-bit keys, despite many academic papers that have been written showing how stupid, quote-unquote, NXP was. Not a single time this actually has been exploited. You could, of course, by just receiving the random number, try your luck and send something random back, trying to guess the right key. But that, of course, takes, again, 2 to the 48 attempts. Doing that over the air interface takes hundreds of years. So in some sense, the HITECH 2 cipher has never been broken in the one application it was designed for. Now, turning our heads to the MegaMoS cipher, which I just said is much more difficult to break academically, it may be a different story. The MegaMoS designers, they optimized the challenge response protocol, moving from 3 handshake to 2-way handshake, saying if the car first sends a challenge and later proves that it also knows the key, why not combine those in one message early on, right? So the car sends an encrypted number, also the encryption of that encrypted number, and then the transponder responds with its version, version of the encrypted number. So for 1, this is not replay resistant anymore, but they didn't seem to care. For 2, though, the car gives you much more than a random number now. It gives you the encryption of that random number as well. And that's where car theft would start making sense. That's where you just walk into a car, you challenge it for a random number and the cryptogram of it, you start breaking it through SAT solver, whatever way you choose, and you steal the car. So this cipher, it's much harder to break and that nobody yet broke academically, at least it's not published, constitutes a much higher fraud value. And that's one of the points that I want to drive home today, that all research around cars has been a little bit off focus so far. We break components, but we don't really understand what that means. Does that make a car good or bad? Do people even care? And it has led to the situation where, for instance, a company like NXP, they heard for many years critique how bad they were, but they can always show to their customers, by our product, it has never led to any car theft. Right? Now, I want to, let me explain this quickly. So there's one thing that may actually start bugging people about the weak transponders, and that is that they become clonable. So you can't steal a car by just walking up to the car, but you can take a key, for instance, valet parking, and you can make a copy. You give back the original key, and you still keep your key. Now, this is a very elaborate way of stealing a car, and probably only it's worse to steal a Ferrari or something. However, people do use this in insurance fraud. So when your car gets stolen, sometimes the person owning the car actually helps the thief, but then they prove that they didn't help them by returning all keys to the insurance companies. Right? So the thief must have stolen it some other way. Now, if they copied it before, that actually hurts them. Also, BMW and whoever has keys that are clonable, they lose money because these keys cost a lot of money, replacement keys for your car. And those machines, they're usually in shoe shops, shoe repair shops. They charge something like $20 for a key, so much, much cheaper than counterfeit. So hopefully, finally, these devices will make clear to NXP and BMW and everybody involved in choosing those cryptographic devices that they have a self-interest in making them better. At the same time, though, in the real world, cars do get stolen in completely different ways, and none of them are related to what we just discussed and what the academic research has discussed. They're not related to the key lengths of the cryptographic immobilizer. Some of them actually do use pretty long keys right now. It's not related to proprietary or standard cryptography. It's not even related to this MegaMoS super bug where now the one thing that makes all the bad cryptographers secure, they leave out in the medium good one. So most of these cars just get stolen independent of any of that. And here's a little video of somebody in Bulgaria. They posted it on the internet for selling a tool that's, you know, when you lost the key to your car type tool. So this is a pretty recent Audi, and it's locked, so it blinks here. I don't know if you see this. So it blinks here, that means the alarm system is on. The alarm system and the immobilizer are actually two different protection systems. And the alarm goes off maybe a minute or so after somebody enters the car. So it's more to protect your radio than the car. But this guy breaks both of them. Opens it, kind of like the lockpick. He had a real key now, but you saw that the plastic part was missing, so the alarm system doesn't go off. And he now connects to the CAN bus. There's a plug, OBD2, connects to the CAN bus, which is kind of like a Game Boy-sized device. Can you read this? So it says unlocking car, so that's kind of the first exploit, and that's not really an exploit. There's a CAN message that just says switch off the alarm system. As simple as that, no cryptographic signature, nothing. But again, this is more to protect the radio, not the car. He again does this just to deactivate the alarm system. But now the real fun starts. Somehow he found buffer overflow or anything like that in the car firmware. And this little device is going to trigger that. But he must have found it in some very obscure function, because what he's doing next now is moving the car into some very weird mode by plugging in and out a few things in the trunk of all places. Somehow that's where peripherals are connected. So he says here, I want to add a new key, right? And now it gives you a nice instruction. What do you have to unconnect? And now this would look terribly silly for a car thief to do. Maybe there's better methods, and his other videos are not that involved. But this is just to illustrate how complicated some of the things are that these Bulgarians seem to be doing with cars, and that we as researchers have no idea how they do. So he unplugs stuff, and this brings the car into some error mode, and then in the error mode he knows some buffer overflow, I suppose, and he triggers, again, through CAN messages, that buffer overflow. He now has read-write access to the EEPROM, and the simplest thing to do is just to delete everything, right? That means that the car is kind of fresh out of the factory. It doesn't have any keys saved yet, and the first thing he wants to do now is learn its keys, right? So he brought a key. It's going to plug in, and then the car, fresh out of the factory, here, 0 of 1 keys learned. It says, learns the 1 key, and he can drive away. Now, that's how cars get stolen today. These are the devices. It has nothing to do with any type of cryptanalysis. It's so much closer to what everybody here has been knowing about, or even actively doing for 20 years, finding bugs in software. Right? So no surprise, though, that such bugs exist. I talked to people in the car from the car manufacturer side a lot, and asked them, do they know about any bugs in their cars? And they say they don't even have the software of their cars. It's all coming from various small suppliers. Oftentimes it's switched around when the same functional part can be produced cheaper by somebody else. They just swap suppliers, and this kind of drives down the quality of these devices security-wise a lot, because nobody can test them for security. The one that we took apart to document what actually happens in this Audi has an instruction set, the same instruction set that was used by the first Game Boy. So it's well supported in IDA Pro, surprisingly. Some Game Boy reverse engineer must have provided all that insight. So that's the type of hardware security the crucial brain of a car today has. Nothing in terms of secure booting, trust chain, not even any hardware cryptography. There isn't any operating system level protections like, say, a phone would have. In fact, there isn't much of an operating system. There's kind of a real-time scheduling system, but it may know threats, but not even processes. So there's no shielding between anything. Once you find a buffer overflow anywhere, there's no memory randomization to make it harder to exploit, and there's no process shielding for keeping you in some type of sandbox, maybe. and I understand from the people I talk to in the car manufacturers that also there's no quality assurance that makes sure that no programming bugs go in. So this is really day zero for computer security as far as real computers were concerned, like Windows 95 type stuff. And that's still today in the car. Now, that may or may not be a reason for concern. One could argue that car theft isn't actually something that a car manufacturer wants to prevent. Right? Insurance companies want to prevent it. They pay for it in the end, but they don't make this decision. Car manufacturer, of course, sells more cars when more get stolen in the end. However, as cars now become much more autonomous, much more interconnected, much more like a computing system, in fact, much more like a robot, there may be many more reasons to break a car brain than to steal it, right? Imagine these cars that are interconnected through Wi-Fi to whoever sits in the car, so they have fast internet and can interact with the car, but also the cars amongst each other, so they can warn each other about dangerous situations. A car that keeps reading through cameras and all bunches of sensors the environment to help you steer better. The new S-Class, it's pretty much a car that can drive by itself. The video from the board member responsible for research that I saw is he's driving around and he's letting his steering wheel go, and it starts beeping, and he says, oh yeah, German law says you need to touch the steering wheel at least once in 10 seconds. Right? So that's a car that you can buy today. And that's a car that still has a shitty little computer like this inside with a Game Boy type hardware architecture and no operating system and no quality assurance about its software. It can be exploited through all kinds of sensors that of course have to pass data and could lead to buffer overflows or whatever type of bug you want to think of, and through all kinds of wide area networks. This car asks for your Facebook password the minute you personalize it, and will read your Facebook messages to you whenever you receive them. So somebody can own your car through a string sent through a Facebook message, potentially. I'm speculating. It is not a bug we found. Right? So that's a car that exists today, and nobody has started finding, documenting, and removing the bugs that exist in the very structure of these devices. So I see this industry going two ways. Some manufacturers will say we're staying out of this entirely. We'll keep building cheap cars and expect people to drive them themselves. And there'll be some other manufacturers that start taking this serious. And hopefully the people who today already build autonomous cars will be among them. But thus far, I've not seen any car component that would withstand simple hardware hacking tools like what we have for even a few days. So we are very far away from building secure cars. At the same time, we keep writing papers about breaking high-tech too. The one thing that still today nobody can steal a car with, and even if they could, it's so much more difficult than buying this tool from Bulgaria and just stealing that way. So hopefully I encourage some of you to get into car research. Use the cryptographic tools everywhere else where you find proprietary research, but use your software tools, use your IDA on car engine control firmwares and find all the overflows and create interesting attack scenarios before the actual criminals do and start, whatever, killing people or influencing their cars in whatever other malicious way. Well, with that, thank you very much for your attention. Any questions? Back there?
Yeah. As you talked about car immobilizers, what about car openers?
Okay, everybody had a question? What's the security proposition of the car remote controls? Oftentimes they're in the same device. So you have a key that's an immobilizer with this passive chip, but also it has some buttons. That's a completely separate device. And most of them use rolling codes. So it's a one-way communication.
So they are invisible.
Well, are they a little bit more secure? I don't know. Depends on what you try to achieve. So a rolling code is exploitable, for instance, the following way. Everybody knows rolling codes. So it's a counter where you always encrypt the current counter value. And the car remembers the last counter value, so you can't replay it. And if the counter is large enough, of course, you'll never kind of wrap around and reach the beginning again. So it's always a fresh authenticator. Devices that you can buy to break those work the following way. They intercept a rolling code instance when it's sent, and then at the end of it, there's a checksum. And at that point, they jam, so the car doesn't understand it. So the person says, oh, that didn't do it, presses again. It sends a second rolling code that's again jammed, and the device very quickly sends the first one with the correct checksum. So the car, let's say, locks. Person walks away, they send the second instance that they captured, and the car again unlocks. To counter that, of course, now they throw in a number that says whether the car should lock or unlock, so there's two different buttons, but it makes it more difficult. It's nicer to just have one button. So these devices are not necessarily more secure, but also they're not really protecting anything. They need to be as secure as a glass window that you can throw a stone through, right? So they're protecting your radio, not your car. Makes sense, right? But if anybody ever wants to do more cryptographic research, look at the rolling code version of HITECH 2. Because of the counters and only one bit flipping in every other instance, it becomes extremely easy to break this from 3 or 4 instances. I don't think anybody has written about that yet, but that would be a nice target for maybe a diploma thesis or master, or whatever it's called today. Like that?
Is keeping the cars dumb away still available to the manufacturers? As far as I know, there are regulations to have, for example, a canvas on the car.
Mm-hmm.
So there's always kind of electronics involved.
So the question, very good and valid question is, can you even still keep a car dumb? Doesn't today already every car have a CAN bus and everything else? Yes, that's true. Cars are, there's no car that isn't electronic by now. And every car has some software, and most of them will be exploitable. However, I meant dumb in a slightly different way. I meant dumb in make it so you can't steal anything from a car. So the car doesn't get hacked because it can be hacked. Maybe we do that as a community for the fun of it. But a criminal will break into a computer of a car to, let's say, steal a Facebook password. If there is no Facebook password, you don't break in. There has to be a reason to break in. And that's the dimension in which I'd like to keep cars dumb until I understand how secure they are. There was another question here. Go ahead.
What frequencies do these car immobilizers work at?
What frequencies are these car immobilizers? They are in the 125 kilohertz range, so it's LF. Supposed to go about a meter, but of course you don't actually need it to be a meter communication. Usually you stick it in somewhere and turn it, and so it's very close proximity. So the antennas are built in such a way that they don't actually work over a meter. In fact, that the longer they work, the further distance they work, the higher the risk of like a man-in-the-middle attack. Right? Also, you can buy those on the internet for some of these. A man-in-the-middle attack where somebody is outside of your house with a big antenna, and somebody else with the other end of that connection is in your car starting it.
What kind of hardware do you use to intercept? I didn't really understand that part.
What kind of hardware do you use to intercept? Yeah, I didn't get into that part at all. That's basically redundant with a bunch of other talks we've been giving on MyFair hacking, on logic hacking, and so forth. It's in this case you can use a Proxmark device. It's a programmable, FPGA programmable, also a little ARM chip on it, RFID reader that speaks LF and is very versatile. To break high-tech, though, in particular, that's not even needed. So 125 kilohertz is the carrier wave. So that's the maximum at which you can possibly transmit information, in fact have that. High-tech shows us that much slower is also fine. And it's so slow that a sound card in a computer can capture it. So to sniff or even like a good sound card in an MP3 player, if that's programmable enough so that you can actually get the raw data and not like an MP3 compressed stuff. So with just a sound card set at 96 kilohertz sampling rate, you can, with a little antenna and one transistor, capture these. Right? There's a good video by Henrik Plötz who did that with not high-tech, but an access control system with his, I think it was an iPod a few years ago. And that was a static system, so where it doesn't cryptographically change every time. He recorded it and he played it back and the door opened. In case you forgot your key. Yeah. Were there any other questions? Well, thanks again.